first, a little retrospective about what I've been doing the last few years. So about 6 months ago, I was at VCF West in the San Francisco Bay Area, and I showed off this exhibit showing my audio-based adapters, as well as, you can see on the left there, it's like a carousel for the adapters, 30 different machines. The year before that, I had these machines kind of stacked vertically with a switcher to go between them. You can see Prince of Persia on a Commodore, and it's either an Atari or Apple, I can't remember. A year before that, I came out with this product, the BackSid. It's a SID replacement, the sound device for the Commodore 64 computer, and so that runs on an ARM chip. A year before that, I came out with the chip tester. You can see the 3 variations here. The latest one is on the right. And this is the BackBit cartridge. This is what I'm going to talk about today. Originally, it was a cartridge for the Commodore 64, and then I made a new version with all these adapters that can go into over 30 vintage systems. And a year before that, I started a YouTube channel. This is kind of what got the ball rolling. And so the origin story of BackBit is that I used my YouTube channel as like a portfolio to get a job working the front desk at a video game museum. And they had all these video game consoles on display with EverDrives, so you could play all kinds of games on them. Except they didn't have really any computers on display, and I was kind of sad about that. And so I looked up what kind of hardware was available to do a similar thing on a computer, and I found these devices, a SD2 IEC and an EasyFlash 3, and they did some of the things I wanted to do, but I really wanted more like an EverDrive type of solution where you could just play every game from a menu. So I decided that I wanted to just build my own thing. And this was like really the start of me getting into hardware. Prior to this, I had a whole career in software. And so I found this article on the Uno cart, which is a cartridge for the Atari that does roughly what an EverDrive does. And I didn't really want to have this gigantic discovery board, so I found on the upper right there, it's a device, you can almost see it under the wire, a device called a Teensy, and that was the 3.5 version, the last of the 5-volt I/O compatible versions. On the left, you can see Al Lasher's. That is like one of the oldest electronics stores in the San Francisco Bay Area that's actually still around, I think, I hope. And then I found some breakout board on eBay, and I wired this up on a breadboard that was like a hand-me-down from my dad, because he was a electrical test engineer, manufacturing test engineer. And I found some level shifters because I thought maybe that would make it work. Except it didn't work. And so I went back to the drawing board. I found this book called Commodore 64 Interfacing Blue Book. And it has this schematic on how to build a expansion port buffer. And back then I didn't really know exactly what was going on here, but I thought, okay, well, why don't I put this buffer on there and I'll give it a try, and maybe that'll make it work. And so I wired in the buffer, and what do you know? I got this game on the screen, and this was the most thrilling thing. I'd been spending about a month kind of just beating my head against the wall every day, trying things to see if maybe it would work. And finally it worked, and so I was very happy. This was a game called Moondust. And so this leads us to, what is BackBit? Well, it's a ARM microprocessor or microcontroller, a system on a chip. It's a chip that has RAM and flash ROM built in, everything you need on one chip. And of course, it's an evolution from what I originally did on the Teensy. Now it's just a bare STM32 chip on a board. And so I've learned a lot over the years on like what TTL is and what CMOS is, what that all means. I decided to do adapters on a device rather than having like 32 different devices, because as an engineer, as a developer, I'd rather just make one thing that does what it needs to. And these adapters are mostly just pass through. You just twist the wires around, except some of them do extra things like power management, connecting a reset pin when there's not already a reset pin on the cartridge port, dealing with copy protection schemes like on the Amstrad CPC Plus, and my Odyssey 2 adapter has a DAC so it can output speech. But fundamentally, what BackBit does, it emulates a ROM chip. It receives address requests and it sends ROM data. It also supports banking and mappers, so the vintage machine can send a request to the cartridge and it will switch out the ROM for a different ROM, and that gives you access to a much larger address space, in this case up to 1 megabyte of data. And it also emulates RAM, which is particularly useful on a machine like the VIC-20, which you would typically need an expansion device where you'd have a RAM cartridge as well as other cartridges together. And then it also does things a little more advanced than that. It does tape emulation on the Sinclair machines and the Tandy Coco, and that's just reading. It also does disk emulation on the Commodore 64 and related machines, on the Apple II, PC Junior, MSX, and Tandy Color Computer, and it does reading and writing, and on some of those it does disk swapping. And this is something that can be extended with firmware updates. My main goal really is, if you want to be able to play a game on one of these machines, I want to be able to support that if it makes sense for the hardware. And then also, this is what I exhibited at VCF last year, which is the PIC-based audio emulation. So there's an additional processor on the adapter to do the Pokey sound on the Atari, SCC on the MSX, which is very basic wavetable synthesis, and then on the Mattel Aquarius, the AY, which is just a few square waves. Okay, this is a full list of the systems I support currently. I don't know if that's big enough to see from all the way in the back. And to be a little more clear on what all these machines are, the yellow ones are video game consoles. The cyan are computers, except you can see there's actually quite a bit of overlap. The Amstrad CPC Plus came out as a GX4000 game console, where it was fundamentally the same machine, just without a keyboard. The Atari XE had an XEGS, which actually did have a keyboard that came with it. And then the Commodore 64 had a C64GS, which was kind of a cut-down Commodore 64 with no keyboard and no cassette port. And so there's really like, if you put a Venn diagram of what's a computer and what's a game console, there'd be a lot of overlaps. And even like the Odyssey 2 has a keyboard, but it can't save programs to cassette, unless maybe someone's done that, I don't know. And particularly, you can see there the ColecoVision and Atom. This was a pretty strange trend in the 80s that you would take a video game console, try to get your customers to get a video game console that was expandable to a computer, and you'd have a little video game system inside a big computer. And I don't think it ever worked commercially. Okay, so how does BackBit connect to all these systems? In the yellow, that's the most common configuration. There's a cartridge slot on the machine. And through the adapters, the BackBit card is smaller than most carts, so it fits in most circumstances. There's some nuances to that. One notable exception to this model, the Apple II, didn't have a cartridge slot, but it had internal slots. And so you could actually stick the cartridge inside the machine. Fundamentally, they're the same thing. It's a hardware bus expansion, but conceptually, for the user, it's a little bit of a different experience. And then the ones in cyan have expansion ports. A few of those actually do have cartridge slots as well, but the expansion port lets you serve ROMs with, lets you serve bigger ROMs, or lets you add RAM expansion. And on the Sinclairs, I guess as a cost-cutting feature, they didn't really have a cartridge port, they had an expansion bus. And the difference between the cartridge port and the expansion bus in that case is that the cartridge port is something you could just plug a ROM chip directly into, whereas expansion bus, you'd need some extra decoding. Okay, this is kind of the secret sauce of how BackBit works. The Vintage system is a client that only is really aware of a single screen of files. You have a wall of text, and you have a list of files, and you can navigate pages, but the client really can only see a single page at a time. It'll request a page of data, draw it on the screen, and then the user can press a key. That key goes to the server, which is actually the cartridge, and the cartridge interprets what key was pressed and dynamically changes the ROM that's being served to the Vintage computer. And it may go offline during this period, so the client might have to wait a little while for the command to process. Okay, and so the worst case scenario of this implementation is on a machine like the Atari 2600 Plus, which came out recently. BackBit does not support cart ripper machines, because the Atari 2600 Plus just reads the cartridge like a ROM and then puts it offline and ignores it from that point on. And so that doesn't work because BackBit needs to dynamically update the ROM continually when you navigate pages and select something. The best case scenario for BackBit to integrate with the Vintage system is that there's an I/O signal on the cartridge bus, so it's very easy to distinguish what's a command and what's a ROM request. It's nice if the Vintage computer can execute code in RAM, so that way it can be executing code while waiting for the cartridge to come back online after a command, because if the cartridge is not serving ROM, it can't be running code from that ROM. And then it's nice if it can accurately wait and see when the cartridge came back online, if it can easily detect if the cartridge is there or not. So one of the snags, like I just said, is what if there's no IO request line? Like, let's say you're on an Atari 2600 and you have a few address lines and a ROM select and a data bus. So the solution there is to use a memory mapped port. You might use an address bit to determine if you're accessing essentially what's an input-output port, or you might just translate a specific part of the address. And if you want to know whether the Vintage computer is writing to the cartridge or reading from the cartridge, you can even use the address to distinguish that. You'd probably just block off a set of addresses. The snag I talked about, if there's no RAM in the machine, there's actually one case where the machine, it's actually the Odyssey 2, where it can't run code from the internal RAM. And in that case, I do something special, which is I bombard the data bus with a no operation, and it's basically just looping there till the cartridge comes back, and then it scans to determine when it reaches a certain address, and then it comes back online at just the right time, so it can pick up. And here's another snag, the floating bus. So if the bus is floating, that means that when the Vintage computer is trying to see if the cartridge is there, it might just get random data, and it might not know really if the cartridge is there or not. You can apply pull-up resistors. That can happen internally in the cartridge. There might be a reason not to do that. The alternative is you can detect, some machines will have a specific set of bytes that are in every cartridge, kind of in the spec of a cartridge for that machine, and you could check for that. Or I could check for specific bytes that are part of the BackBit code, or kind of a gnarly method that's used on some of the Ataris. You can read memory twice, make sure it's the same, and that it's not randomized, and also make sure the memory is not all zeros or all essentially binary ones. So these are various methods I've had to use to detect if the cartridge is there, if it came back. Okay, these are the CPUs that I've had the pleasure of basically writing code for. You can see that there's 8-bit CPUs as well as 16-bit CPUs, but these 16-bit CPUs actually lived in the 8-bit era, so they typically integrated with peripherals that operated in 8 bits. And so in some ways, 16 bits was kind of a limitation rather than an improvement, because there was more overhead and more focus on other things that kind of didn't need to be there. Okay, so I'm going to get into the weeds here. These are some machines that have a MOS 6502 or variant. You can see there's Apple II with a Commodore 64 and an Atari 7800 on top. And so these are actually pictures of machines I have in my office. So with the Apple, Atari game systems, and 8-bit computers, and various Commodore computer, or pretty much all the Commodore 8-bit computers, I guess, with the exception of, well, the PET did have that, but that's not something I've worked with yet. Here's some code for copying a section of memory to another section of memory. It's a lot of instructions. It's somewhere around 30, I think, lines of code just to copy memory from one place to another, and that'll come up in a little bit. Here are some details about the 6502. It's got 3 registers that you can use for computation, A, X, and Y. There's an accumulator and 2 index registers. One weakness of this processor is that it doesn't have an I/O request line. It has memory mapped I/O. So it's like that snag I said earlier. It's not so easy to determine if it's requesting data from the cartridge or not, or if it's sending a command. An idiosyncrasy of this processor, it has a decimal flag. This allows you to do binary coded decimal arithmetic, which is not commonly used, I don't think, unless maybe you're drawing numbers on the screen. And it's something where if it's enabled and you don't want it to be, it might do strange things to your code. And it's, in most cases, just kind of annoying. A superpower of the 6502, it's got a 0 page. And that means it's essentially 256 memory mapped registers, or 128 16-bit memory mapped registers. And it allows you to do, it kind of makes up for the fact that you have only 8-bit index registers X and Y. It allows you, it basically beefs up the processor to be able to do a lot more. The 6507 was a cut-down version of this, used in the Atari 2600. They basically just cut a bunch of the address lines. There's expanded versions of this, 6510, which was used in the Commodore 64, 8502, which was used in the Plus 4, and they basically just added some pins for input-output, which aren't actually I/O request lines, but they're just like an I/O port. The NES had a variant of the 6502, which had audio and some other features built in. The Sally was used in the Atari machines and had a halt pin added. Okay, the next processor, this is probably used in the most machines that I've dealt with, a very popular processor, the Z80. And this is the superpower of this processor. Remember the code I just showed you with like 30 instructions? This will basically do the same thing in just 4 instructions, and really everything happens in that LDIR. It says, take the values of these 3 registers and copy the memory from this place to this place. And so it's very useful. It's not necessarily a lot faster, but it's just a bit easier to code with. It's got these register pairs, which essentially act as high and low for an 8-bit low and 8-bit high register, forming a 16-bit register. A weakness of the Z80 is a lot of the instructions take a lot of cycles. So like on the 6502, you might have 6, maybe 7 at the most cycles for an instruction. Here you have up to 23. An idiosyncrasy of the Z80 is the accumulator bottleneck. If you want to do arithmetic or bitwise operations, you typically have to do this through the accumulator. And so even though it has like essentially 7 general purpose registers, you still have a bottleneck of having to go through the accumulator. The NEC Micro PD 7801, it's kind of a variation of the Z80. And there's a little code sample. Doesn't have to mean much, but just showing you what the code. Oh, I'll come back to this in a minute. It was essentially a competitor to the Z80. Similar set of registers. Instead of F for flags, it had V, which means something else. A weakness is that it's obscure. There's only one machine I know that, one commercially available machine, the Epoch Super Cassette Vision, that used this particular chip. An idiosyncrasy, it doesn't have the ability to do a comparison and then jump somewhere if the comparison is true, or branch if the comparison is true. Instead, if you can see in the small text here, EQI or NEI, that does a comparison and then it skips the next instruction if that condition is true. So you will typically see these comparisons followed by a jump. It's just a little idiosyncratic, that's all. A superpower is that there's a Renesas 78K family of microcontrollers that is still in production, still evolving today, but doesn't really live in the gaming world. Okay, Motorola 6800, 6809. This was actually what inspired MOS to make their 6502 chip. And you can see a difference between the 6800 code and 6809. Those 2 blocks of code do the same thing, but the 6809 adds a second index register, the Y, and it also adds an auto increment. So you can do a lot more in fewer instructions. And it's got 3 registers, 2 accumulators, and a single index register, or for the 6809, 2 additional index registers. And a weakness, again, the memory mapped I/O, which is probably why the 6502 was designed that way, because they were modeling it after this. An idiosyncrasy is there's limited indexing, particularly on the 6800, because there was only 1 index register. So if you want to copy memory from one place to another, you have to store those indexes in memory. You can't use registers, which slows things down. A superpower is that Hitachi came out with the HD 6309, which was a drop-in replacement for the 6809, which had a whole additional set of instructions. So it was kind of like an upgrade you could put in any machine that already supported the 6809. Okay, this is somewhat obscure. Signetics 2650 was used in the Ace-Tronic, which was actually an evolution of a machine made by Radofin, which was also cloned by Interton. And then there was also a machine, the Emerson Arcadia, which used the same processor, but a different display chip. And this is an example of some code. This is something I'll touch on later, racing the beam. So this is all the code it needs to basically every frame it draws the screen. It's got 4 general purpose registers. Its weakness was poor marketing. If only they would have marketed better, maybe more systems would have used it. Idiosyncrasy, condition codes, not flags. This is maybe an idiosyncrasy of mine, but the condition codes are essentially, there's 2 flags. It's like an equal flag and a negative flag that get combined into a condition code in a weird way. Read up on it if you're interested. A superpower, flexible indexing. TMS, 9900 or 9995 in the Tommy Tutor, which was a slightly evolved version, but You probably all know of the TI 99-4A. That was the main case. Well, obviously TI wanted to use their own processor. Here's some interesting looking code. And actually this is to write data onto the screen buffer. Okay, the registers are all memory mapped, which means they're slow, and even slower if the memory is external to the processor. An idiosyncrasy is that while the processor did have 256 bytes of RAM on board, for some reason they decided that was enough for the whole computer, and the TI-99 only came out with the stock of 256 bytes. Superpower, it was sold at a loss. Obviously not a superpower for TI's computer division, but great for the consumer. General instrument, note that there's not an S after instrument. CP1610, this lived in the Intellivision. 16 because it was a 16-bit processor, and 10 because instructions only use 10 bits. The registers, 16 general purpose 16-bit registers, so pretty versatile. A weakness, proprietary ROM interface. You couldn't just put a regular ROM cartridge in the Intellivision. It had to be very specific to the bus they used. I think there were like 3 bus signals that did different things. Idiosyncrasy, decals. So the ROMs that plugged into the Intellivision had 10-bit data words, which is a total anomaly. Usually it was 8 bits back then, but 10 bits, which was 10 bits to specify the instruction, or 8 bits to specify data and 2 bits that are not used, because who needs 10 bits of data when you got 8 bits? Okay, superpower, full 16-bit ALU. All right, we're almost done here with the processors. Intel 8088, which lived in the PC Junior. Registers, AX, BX, CX, DX, 16-bit registers, which with ability to access the high and low 8-bit components. A weakness, of course, the cut down 8-bit external bus for a 16-bit processor. So even before it gets out the door, you can't use all 16 bits externally. Idiosyncrasy, not really a cost saver, because yes, they probably saved a few bucks on the chip, but the machine still cost a fortune, and most people couldn't afford one, so they didn't sell a lot of these. Superpower, the PC Junior, however, was the first PC or PC clone that had good color and good sound, and good is, of course, relative to the time. And Tandy decided this was a great model for playing games, and they made a whole line of computers that was much more successful, but kind of very similar hardware roots. Intel 8048 sounds similar, but is completely different. It's more of a microcontroller than a microprocessor, kind of something meant to do less, and came out earlier. This is very unusual. It has an accumulator and 8 memory mapped registers. It can't run code from RAM. It's very limited in how it can access the data it has, which I guess is kind of typical for microcontrollers of the time. Idiosyncrasy, it can read data on the current 256 byte page or the third page out of a 2K memory bank. And a superpower, and this is ironic, is that it has 2 memory banks and it can only live in one at a time. So you have to constantly, if you want to have a 4K application, you have to pretty much switch between the banks manually. The RCA 1802 was in the Studio 2, and there was also a Studio 3. That's actually a Studio 3 machine there, which is the same machine, just added a little bit of color. Here's some code to render an image on the screen. 16 general purpose 16-bit registers. That is a lot. Very versatile. However, 16 to 24 cycles per instruction. So the clock speed is actually cut down by a factor of 8, which makes a 1 megahertz machine really 1 or 200 kHz machine. So pretty slow on the processing, even if it's versatile. Superpower, it went to space. I guess it was very radiation proof. All right, we're almost done here with the processors. Fairchild F8 was in the channel F. Here's some code to draw the screen. Registers, an accumulator and an indirect scratch pad. A big weakness, it has a proprietary ROM interface. You can't plug any regular old ROM into it. It has 32 different bus states that the cartridge ROM has to obey. Very complicated. Superpower, though, it was the first cartridge-based console to exist. Okay, we're done with CPUs. You can breathe now. Video processors. These are the video processors used in all those machines. A special case is vectors. The Vectrex had vectors instead of a bitmapped display, using a single DAC and a multiplexer to control X, Y, and I guess brightness axes. The green was beam racing. So those machines didn't have enough memory to store the contents of the entire screen in memory, so the code had to render the screen while the beam was going down. That's what racing the beam is. And that makes coding kind of a nightmare. The cyan are very easy to deal with because they can render characters. You just put characters in the screen buffer and they're on the screen. The purple are bitmap only, meaning you or the system BIOS has to manually render characters onto the screen. Okay, so this is the big reveal. What is the BackBit operating system? It's basically just a file browser. It starts with the splash screen. The BackBit cartridge needs to start up very quickly. It needs to read its SD card and initialize the real-time clock. It needs to get started very quickly because if there is no reset pin on the cartridge port, then it has to be available and look like a ROM cartridge by the time the machine has completed starting up. Weird case with the TI-99, there's a system menu, so the computer will start with its own splash screen and then say, choose an item from this menu, and you can choose BackBit. And so some nifty features on some machines, as you can see, like tells you what version of the kernel is running on this +4, tells you that it's NTSC, tells you the version number of the firmware. This is the file browser on some machines. You can see on the lower right there, it's RCA Studio 2. That is the smallest set of pixels on a screen that I support. I think it's like 64 by 32, somewhere around there. And so on all the machines I support, you can see 3 up to 23 files on each page. You can see :B, that's how I decided to implement the BackBit logo on systems where I couldn't remap the characters. You've got the time of day and the current directory. Line navigation, so without making a request back to the cartridge, the client can navigate up and down in the current lists, and then it will send a command to navigate pages. The cartridge itself stores up to 1,000 items in the current folder. And of course, it may go offline while navigating if it takes time to look up more files on the SD card, or if it takes time to load one of these programs. The search is only available on machines that have a keyboard. You can just type on the keyboard of the machine file you want to play, and the response is nearly instantaneous. I have these context menus, so it's 4 different menus: utilities, properties, saves, and tools, and it all does different things on different machines. I try to make this work on as many machines as possible, so Basically lowers the learning curve. If you just want to fire up an old machine and run something, you don't have to think too much about the nuances of that particular machine. You just fire it up and pick a title, and if you want to change the time, you can do that. If you want to change the amount of RAM expansion that you give the VIC-20, you can do that on the PC Junior. I can use Quicksilver to make it start up faster. The saves is pretty useful because if a game supports saving, you can have versions and you can have save points. So if you're playing an adventure game, you can save it at various points, and the versions will all be managed by the BackBit Operating System. Commodore 64, I have this neat thing called burn and rip, which is analogous to CDs, but happens with floppy disks. Okay, so the biggest frustrations that I've had to deal with over the last 5 years or so, the 3D printer isn't working. That really gets to the core of my anxiety. Racing the beam screen rendering is pretty annoying. Emulating a disk controller is pretty annoying for a bunch of reasons that I won't go into. Things that blow up from 12 volts going where it's not supposed to go, that's annoying. Disassembling an Atari 400 or an Atom, if you've ever done that. Commodore 64 clock jitter. So if you've ever looked at a Commodore 64 clock signal on an oscilloscope, it's not pretty. Lack of love for some machines like PC Junior. I don't know, I have a special place in my heart for the PC Junior because it was like that, when I was using my Hercules monochrome PC, this was like this cool machine that could play games with good graphics and good sound, and just seemed like a unicorn. Some of my greatest achievements, the things that I'm happiest about. So I taught myself practical electronics. Like I said, I used to be software engineer, and it's kind of exciting to see this other side of the tech world that was kind of living underneath what I was using all that time. Learning to print ABS. This actually took me even longer than making the first prototype for the BackBit cartridge. It took me about, I think, a month and a half, and my mother nearly gave up on me, which says a lot. Successfully repairing machines. So all of the machines that I support with BackBit, not all of them, but a good number of them came to me in not working condition, and I had to figure out what was wrong with it. It's usually the power supply, but some other things too. ARM bootloader. So it sounds simple, but it's complicated. This is why most people use Arduinos and Raspberry Pis, because they don't want to write their own bootloader. And it cuts out the middleman, that's all I'll say. REL file support. There are these nuanced files for the Commodore 64 that were not used that much, but used a lot in this one game, Commodore 64 Castle Wolfenstein. Recovering lost pieces of my childhood. So it's like that game that I played as a kid that my brother thought was unimportant and like sent away to someone else. And I said, what'd you do with my game? I was very angry. I talked about that in my first YouTube video. Yeah, just bringing back things that were exciting from childhood after I got so burnt out of being a video game engineer in the software industry. And then finally, FPGA prototyping. So I don't have FPGA products that I'm selling right now, but I'm trying things out, and it's exciting to go from just using microprocessors to FPGA, because it's just like you have exponentially more things you can do. And so it's just kind of where my brain lives. That's what excites me. So that's it. You can ask me whatever you want. If you're curious about anything, burning questions.
So you've been designing hardware and software for all these retro systems. Entertainment.
Any new hardware on the horizon?
So the things I'm working on, so I have the backsit, and I made a prototype of an FPGA version of that. It's almost the exact same thing. It's like maybe slightly higher quality, but you have to be an audiophile to really even hear the difference. And I have a prototype adapter for the Nintendo Entertainment System, which is going to be added to this list probably at some point. That machine's unique because it has 2 data buses, one for the processor and one for the video, and that required a bit of extra circuitry. One thing I'm really interested in going into is in the audio world. In particular, I want to try and connect various vintage machines to synthesizers. And of course, I know that that has been done, but I'm trying to make it easier to do. Yes?
So you have the different adapters for the different systems. That's just mostly an electrical adaptation, right?
In a lot of cases, but there is sometimes additional circuitry.
I asked, is the main cartridge have intelligence in it to know sort of which system it's in, so it can adapt like these complex ROM protocols for some of the systems, or is that in the adapter?
Yeah, so it is, the BackBit does need to detect what it's connected to, and there are various techniques I use. Originally, it just kind of guessed in a heuristical kind of way, but then I realized with the amount of machines that are connected, it gets very tricky to guess, and so there's one signal it can detect, and then from there, there's a set of pins that are either high or low that kind of essentially act as like a toggle, so it knows for sure.
It tells it what system it's essentially attached to.
Mm-hmm.
But the code to handle the different systems is actually in the main cartridge, right?
Mm-hmm. Yeah, most everything's in the main cartridge. Yes?
Talking about synthesizers, I had the good luck to work on the Amiga back when we were designing it. And it didn't have a freestanding synthesizer chip. What it had was 4 channels of basically DMA audio. You could take, each channel could be 2 bytes up to 8K bytes. And it would scan them in DMA. You could set how fast it read them. And it had 8-bit digital analog converters times 4 channels. So I've been collecting Amigas because at some point I want to try these things. I got to design it on paper. I didn't get to play with lump story. If you're curious, I can send you an article about how it works.
Yeah, I am very fond of the mods. My kind of introduction to that type of computer audio was actually on PCs. I was using a Pro Audio Spectrum, and it had a mod player, and that was, like, at the time, really exciting to me. So yeah, I definitely have a fondness for that whole genre of music. Yes?
Yeah, this ZX81 adapter work on TS Windows.
Yeah, Timex Sinclair 1000, yes. Timex Sinclair 1000 essentially is almost the same thing as the ZX81. It's got an extra K of RAM. Yeah. That was actually, coincidentally, my very first computer. So it has a special place in my heart. Yes?
What CPU do you actually enjoy working? What's your favorite?
I mean, I actually kind of like working with ARM, actually. I write a lot of code in the ARM assembly that goes on the cartridge itself, and that's been fun to learn. Yes?
I have a bunch of students at the University of Washington who are rebuilding an ARM on an FPGA because if we want to teach microprocessor system design, we like to teach logic analyzers. But nobody makes modern ARMs that don't that do expose the buses. They're all hidden inside I/O or hidden inside cache memory, so you can't see what they're doing. So my students are specifically building a machine that exposes multiplex cycles to data buses so you can watch them work as a teaching tool. It's fun.
Well, I think that's what's exciting about FPGAs. You can reproduce stuff like that and tear it apart and hack it out. One more minute. One more question. Anybody own any synthesizers? Casio, Yamaha.
I have one more question.
Yeah.
On MOD files, since you brought it up, I'm intrigued with, can you add on Light 2 computer, the little tiny computer? It's a little bit bigger than a credit card size, 8-bit, 20 megahertz little machine. They've got a program software running right now. It runs MOD files. Where would you think a good primer to learn that? The MOD system. I know there's a website that holds, it's a repository of mod files. But where could one learn, you know?
Go on YouTube and type in trackers. All right, thank you, everybody.